This session we're going to be talking about biomass feedstocks, and firstly, before we begin with that, I want to show you a really good resource which will be useful for you to evaluate the feedstocks that you're going to be testing out. Okay, on the screen right now, I know it's a little bit kind of low contrast, but this is the only thing I'm showing, so I have this on screen. There's a database by ECN called Phyllis, right? And they have data on thousands of feedstocks. I mean, everything from wood chips to like human bodies, okay? And you can basically go into their database and look up whatever feedstock you want, and most of the items have indications of fixed carbon content as well as ash content, volatiles, and all that. So let me pull up the URL for you real quick. See if I can get this. Everyone, if you're taking notes, take down this URL. This is very useful. It's www.ecn.nl/Phyllis2, and what you do is you come down to here, go into their database, and do you see on the sidebar here? There's this entire list of items that you can pick from. They have manures, algae, chars, husks, shells, pits. Let's take a look at some of the items in the husks, shells, and pits.
What's the URL again?
That would be ecn.nl/Phyllis2. PHYLLIS2. Okay, so just as an example, I'm just going to go through one of these guys. Under the husk, shells, and pits, they have almond, cacao, coconut, hazelnut, olive, others, peanut, rice, sunflower, so on and so forth, right? So let's take a look at coconut. So coconut fiber, husk, pith, shell, so on and so forth. Under shell, they have all these different studies that have broken down the contents of coconut shell. So if you click on one, it will load it, and you can take a look, the publication, the people who worked on it, where it was published. Over here, the proximate analysis, moisture content, ash content, volatile matter, fixed carbon, all of that stuff is listed over here. Can you guys see this decently?
Yeah.
Okay, so this is going to be a very useful tool if you want to pre-qualify your feedstock. So let's say you have some sort of, I don't know, like juju beans or something like that, and you want to find out whether or not they are qualified for use in the power pallet. And you look it up, and it turns out to have like 20% ash or something like that. You can pre-disqualify that feedstock by just looking up the data that's already been gathered based on studies that have been done, right? A lot of these items have multiple entries. If the data is missing from one entry, look it up in another one. Rice husk has been beaten to death. You could look. Some of them don't have data on ash. Some of them do. Some of them don't have data on fixed carbon. You know, just find one that has one. And if you are using an unusual feedstock that is entirely like not listed here, then well, then other protocols are in order, right? So. We know for sure that the power pallet is compatible with cellulosic biomass, right? Basically woody biomass, right? I'm going to break down my discussion into a couple of, in two major categories. We're going to talk about chemical compatibility and then physical compatibility, right? Actually, you know, physical compatibility is probably easier to talk about. So we know for sure that cellulosic biomass will work, but it will work chemically, but it doesn't necessarily work physically, right? So let me give you an example. Open pine cones, right? Pine cones they're woody, right? And there's plenty of void spaces, but the problem is open pine cones will lock together and will just not feed. So in that case, you have something that's chemically compatible, but not physically compatible. And in order to have the power pallet be a practical, you know, biomass power generator, you need to have fuel that's compatible both ways. So let me see if I can pull up an auger insert real quick. This is the auger that's sitting at the bottom of that drying bucket, right? So if you're going to feed feedstock into that machine, you have to make sure that it can actually get pushed by this. So some folks have, you know, scrap wood, and they're thinking, well, this is about the size you want, right? 1 inch by 1 inch or so. But as you can see, this will just straight up jam up the auger. You'll get it doesn't necessarily fit in. You can't guarantee that it will slide in exactly like this and get pushed along evenly, right? So the first qualification is it has to be able to fit into this, right? Every single power pallet crate that we ship out has meshes that are attached to the side. And previously, if you remember from the demo video, there was some of that sifting action going on from those meshes. If it will fit through that mesh, it will be compatible with this auger. Okay, so that's the first thing I want to point out. Okay, so cellulosic biomass, right? This is basically paper poo, right? Made out of some sort of paper. It's cellulose, but a lot of the folks who want to produce pellets and stuff, they have a machine somewhat similar to this. Sometimes you'll produce pellets about this size. It's been repeated previously, but it's worth repeating again. If you have a pellet type material, you have to make sure it's really dry, because one of the risks with pellets is that all of the moisture driven off during the drying stage will condense on the stuff above it. And when you steam pellets, they tend to loosen up and crumble. And when they crumble, you run into the other physical incompatibility, which is that crumbled material doesn't support the void spaces needed to carry out combustion and tar cracking. Okay, any questions so far? Bear?
Just point out as well, when you're pelletizing compacting materials that much, once you expand or once you apply steam, you'll go from that 5 times densification back down and end up filling the void space.
Yeah. Okay, so if anyone didn't hear Bear there, he's basically saying that the heating and the steaming of these things will cause them to swell. And sometimes your pellets might be the right size going in, but then they swell up from the steaming, and it's like popcorn. It's just no longer physically compatible, right? Okay, so with the matter of physical compatibility, it's not just the size. You have to make sure your material doesn't jam up and lock. So over here, what we have is we've got a bunch of laser cut pieces of wood from well, ranging in size from things like this down to little nuggets, right? But as you can see, this material flows fairly easily. It doesn't lock up too easily. So material like this might actually be compatible. What really causes a problem is if you have a chipper that produces shards of wood, right? If you're chipping wood, one of the things we recommend is chip it and then dry it. If you chip wood that's really dry, it tends to shatter into these little bristly filaments, and you're going to get constant fuel jamming either in your reactor or in your hopper. Okay. I'm going to start laying out some of these guys. If anyone wants to pass these around, these are too small. These are examples of what not to do. Right? You want to just pass this around? These are items that you would find post sifting. That's stuff that'll come through the screens, right? Now, on the topic of chemical compatibility, we want stuff that will produce a decent charcoal. If you run your little search through the ECN Phyllis database and you find that your feedstock has sufficient fixed carbon, right? That is necessary but not sufficient. The fixed carbon needs to be able to form a charcoal that will permit the percolation of gases, right? So something like grass, it might have sufficient fixed carbon, but if the charcoal that's formed out of that will just crumble when it gets run by that auger, then that's not physically compatible after the pyrolysis stage, right? So that's grasses. Now, do you mind if I just lay these up here, or does anyone want to see examples of what not to do further? I'll leave these up here for now. Okay. So now, of course, this is kind of like the disqualifying run, right? Everyone knows about wood chips, so let's talk about some of the other things that people were interested in, such as rice hulls. This is rice hull, right? For those of us from market areas where you've got tons of rice, I'm supposing Myanmar has tons of, yeah. This is not really compatible. As we had mentioned before, I think, rice hull is about 20% silica. So if you run material that's extremely rich in silica through our reactor, the carbon burns off, but you end up with clinkers. The silica will actually fuse at the temperatures that we achieve in our reactor, and your reactor is going to fill up with this stuff. This is not from rice hulls. This is from simulated human waste, if I remember correctly, right? You
can leave that.
Yeah.
It's sterile now.
Yeah. Okay, no, because we've had folks where we warn them not to use some fuel, and they're just like, well, what if we, so materials that are really rich in silica will form clinkers, right? Let's progress through. This material here is basically charred rice hulls, right? Charred rice hulls may have a higher carbon to volatiles ratio, but the ash is still in there, right? So if you have a particular material and its fixed carbon to volatiles ratio is wrong, and you maybe torrefy it or whatever to try to raise the carbon to fixed ratio, the fixed carbon to volatiles ratio, it's not necessarily going to work. You definitely have to check the ash content. An acceptable ratio of fixed carbon to volatiles is, we'll use wood as an approximation. Wood's about 20-80, 20% fixed carbon to 80% volatiles. If your material has really, really good void spaces, but has higher volatile content, the void spaces would support tar cracking, right? If I remember correctly. And by supporting better tar cracking, it might be able to tolerate a higher volatiles content. So if anyone didn't hear, the thing that Bear pointed out just a second ago was that the shells of almonds tend to be pithy rather than woody, right? They tend to be like fibrous and squishable. And the material that really is just known to work better is the woody type material. Yeah? Okay, so one more matter on the topic of physical compatibility is density, right? So here I have a corn cob. Corn cobs char very well, but they're also very lightweight, and they lock together because they're extremely high friction, and they don't necessarily fall under their own weight. So if you have a hopper load of this stuff, firstly, the low density means that you're going to run through this material fairly quickly if it actually goes through. Secondly, you may end up spending a lot of time breaking bridging in the reactor and in the hopper. Question?
Chip them or something?
Well, here's the thing: we ran chipped corn cobs in our 100 kilowatt experiment, and even when chipped, they were constantly jamming because they're not very heavy and they're high friction. It's almost like Velcro up here.
Remember, there were some other driving factors there that we still had a lot of the husks on it.
Yeah.
And it's the husk, the strings coming off of it, that winds around in the fuel bed and holds it together. Mm-hmm. We saw a reasonable flow, and we just had the raw cobs.
Just like strictly the cobs. Okay.
Yeah. Yes, they are light, but they're such nice shapes that they do flow reasonably. The ones we were working with were also much smaller than that. But as soon as we had any of the husk on it, that became just twine in the bed that would hold it together.
We ran the corn cobs in 80 without any problem. They go through.
Okay, so the qualifying factor being you have to completely dehusk it, remove all the fibers and the corn silk, right? Okay, so let me see if I can pull up some examples. So these, if I remember correctly, these were the coca bean husks.
They look like
Liberia?
Yeah.
No, that's palm nut shell.
Palm nut shell.
Yeah, it's not coca.
Yeah.
It's not coca.
Okay. Now, correct me if I'm mistaken. This ran as a suitable feedstock, right?
Yes.
Right. So I lost where I was at. In any case, let's pass this around. This is an example of a.
But it has such a high fixed carbon vol ratio, and Yeah, okay. The issue in that, again, was that it burned very hot, and even though the minerals in it are relatively low, we got a lot of sliding for temperatures were so high.
Okay, so when we run the feedstock, we recommend that you actually run the machine with feedstock that has a moisture content that is 25% or less. 30% it'll tolerate it at load, right? If I remember correctly, right? So every one of your power pallets comes with one of these little stabby tools, right? This is a moisture meter, and what you basically do is to determine whether or not your material is dry enough. First, install the battery. So when we state that moisture content, we're actually stating that on a dry basis. So you guys know about the calculation of moisture based on a dry basis? You're measuring the weight of the material as is versus the weight of the material when it's completely dry. And one way to completely dry the material is to get a small glass bowl and stick your feedstock in there and microwave it. Just microwave the heck out of it until it's completely dry. And then you compare the weights. Bear?
You want to pulse it shortly to actually get pyrolysis if it's moist enough. Cause problems in your microwave. It's very slow. So you want to pulse it, and there's actually instructions we have for that.
Okay.
Low hat.
Huh?
Low hat.
Yes. So when you dry your feedstock to the point where there's no more moisture to be driven off in the microwave, divide the weight of the two of them, and you have an approximation of how much of that weight on a dry basis, meaning you're dividing by the dry weight, how much of that weight comes from the moisture in your feedstock, right? And you want to keep that if you're taking notes. This is repeated everywhere, so you know. But the moisture content should be 30% or less. 25% or less is more ideal if you're running at a lower load, right? But barring that, you can use one of these. So grab your feedstock.
Suit your knees.
Huh?
Suit your knees.
Oh, my knee?
By the way, it tops out at 39%. So
Yeah. So this piece is reading 20, right? So what you want to do with your feedstock is you don't just want to take one piece and presume that that estimate is fair for the whole bunch. You want to pretend you're a statistician, you know, and take a sampling and average out the readings that you're getting.
Note as well that really works over woody material, wood chips, and things like that. It's not going to both stab a walnut shell very well or give an accuracy.
Right. So every power pallet comes with one of these, right? So this is how you'd go about determining the moisture content of your feedstock. Now,
So Austin, assume I have a woody feedstock.
yes.
And it's in big chunks like a tree or a branch or something. And I want to use that in a power pallet. How would you suggest that I prepare that fuel for a power pallet?
Okay. Well, firstly, chip it and then dry it, as I mentioned before. But if you're getting to the point of chippers, there are disc chippers and then there are kind of spiral-bladed auger chippers. The disc chipper will give you a larger distribution of sizes. An auger-style chipper like the Lament will give you a much more consistent chunk, right? If you're using a disc chipper, you'll have to sift your material, and the siftings are not necessarily just waste because in the fuel filter, you need to have sifted material of different gradients. You need to have coarse material at the bottom, grading all the way up to fine material at the top, right? So I'm presuming most of you guys would be using wood in your power pallets, right? Just out of curiosity, who here has a chipper? And if you do, what type of chippers? What?
I don't own one, but on projects we just use commercial chippers, and I believe they're disc chippers.
Disc chippers.
I
Those,
also heard there's a drum type chipper. What are those?
a drum type chipper simply has the blade on a different axis. And the drum type chipper, generally you can adjust the bite somewhat, but you're still going to get a pretty big distribution of chips.
And they're also going to be very splintery. They're biased towards long, splintery.
So you suggest using what types of chippers?
For cost effectiveness, I would recommend the disc chipper. That also gives you material that you can sift when you sift your final chippings. It'll give you material for your fuel filter, for your gas filter rather.
So if I'm using a disc chipper and I'm trying to optimize the size coming out of it, what are my options?
Disc chippers generally have an adjustable bite, right? You can insert shims behind the blade and sort of get it to bite off different depths. And you can kind of calibrate that bite until you're getting a size distribution which is fair for your reactor, right? And that's generally 1/2 inch to 1.5 inches.
Once I have it chipped and I'm like trying to size separate it, what are my options for screening and size separating?
Hardware cloth is generally the most cost effective. We include hardware cloth samples on we include some screens on the side of the crating for the power pallet for reference. If you remember from that video that we showed previously on how to pack the filter, in the video I prepared that. There's some demonstrations of the sifting. We were sifting it using both window screen size material for the very fine material all the way up to the inch squares screens for separating out the fuel grade feedstock. Right.
Are the chippers you guys speaking of PTO driven or are they cast driven?
The disc chipper, that's just the style of the blade. They can be either. Most of the companies that sell chippers out there sell them either with or without. It really depends on the brand. Okay, so any questions so far on the feedstocks and feedstock preparation? How about manure? The problem with manure is manures tend to be high in ash, and they also tend to have a lower energy density because most of the energy has been taken out of it by the animal producing it, right? Generally, I'd recommend not using manures. If you're doing manures, use them on an experimental basis if you're investigating the manure, right? The ECN database has a huge list of different types of manures from different animals. And they actually have processing information on there. So I wouldn't entirely rule out manure as a whole, but so far from everything we've encountered, manure does not work particularly well. If there are no more questions, I cede the floor to the next.
I'm going to survey what fuels people are interested in using.
Okay, so who here is using agricultural waste? Just to get a sense. What sorts of agricultural wastes are you working with?
8 acres of roses.
Roses?
Yeah. 8 roses.
The stems of the roses.
Plants.
Wow. So the stems are 3/8 of an inch and down.
Yeah, 2 inches and down.
So in that case, I wouldn't advise so much a chipper as much as a chunker. You've seen those machines which will basically just cut chunks out of rod type material?
No.
There are processing and there are machines which will basically just chunk limbs of trees, and material like that would probably be better chunked than chipped.
There's a page in the wiki on our website that has a big index of chippers, chunkers, loppers, shredders, all of these different machinery types. Realized from stuff off the shelf for commercial, stuff off the shelf for low end, and DIY methods to make